Hey guys, in this video we're going to be looking at our next type of proof. Now we're going to be channeling our inner Sherlock and doing some deduction. So deduction is when we work through a string or a chain of logical arguments that help us arrive at our conclusion, thus proving our conjecture or statement. So this is exactly the sort of thing that Sherlock is doing when solving a case. He works through one clue which leads him on to another clue which leads him on to another clue, eventually solving or proving what he's trying to solve or prove. So we are doing that, but mathematically. Now, first off, we're going to start with a non-mathematical example, and then we will work through some mathematical examples. So, first of all then, the conjecture that we want to prove here, non-mathematically, is that Spider-Man lives in New York City. So, how are we going to do that? Well, let's work through first of all what we know. We know Spider-Man is Peter Parker. Now we know Pete Parker, let's call him P, lives with Aunt May. Now we know that Aunt May lives in Queens. Now we know that Queens is a part of New York City. So if we follow through that chain of statements, we can actually conclude then that if Spider-Man is Pete Parker lives with Aunt May lives in Queens is a region of New York City, we can then say this implies Spider-Man lives in New York City as we originally wanted to prove. So this is a bit of a cheeky one, but it works absolutely. We have deduced that Spider-Man lives in New York City using information that we know. So now we're going to take this idea and apply it to some maths. So I should say here as well, at GCSE we probably did some algebraic proof where really we were doing proof by deduction without knowing it. So it's not always algebraic. Sometimes we could just use words. Sometimes though we are going to get algebra involved. Okay then, so the first mathematical conjecture that we want to prove here is that the sum of any two consecutive square numbers is odd. So when we're talking about sums, we are adding together. When we're talking consecutive, we mean one after the other. So for example here, 1 and 4 are consecutive square numbers. So 1 plus 4 is 5, which is indeed odd. So that's good, it does work for 1 and 4, sorry. So the problem is though, how can we prove this without doing every single pair, which is impossible? Well, first of all, let's think about our first number. Now let's call this number n. Then what after n is the next number? Well, it's n plus 1. So these two guys here are our consecutive numbers. Now to get our consecutive square numbers, we are going to square them both. So if we square n, we get n squared. If we square n plus 1, we get n plus 1 squared. Now we have expressions for our two consecutive square numbers, and the sum is saying to add them together. So the sum of our two consecutive squares well, that's going to be n squared plus n plus 1 squared. So if we now expand this out, we get n squared plus n squared plus 2n plus 1. Now if we simplify that a little bit, we get 2n squared plus 2n plus 1. So this is our sum of two consecutive square numbers. We want to show that this is always odd. How can we do that? Well, if we look at the algebraic parts here, we have a common factor of 2. So we can write this as 2 lots of n squared plus n plus 1. So that's another way of writing the sum of our two consecutive square numbers. Okay, well, what can we deduce now then? Now that we've got the sum of two squares written in this form, well, we've got 2 multiplying the bracket. Now that means whatever is going on inside of the bracket, odd or even, if we multiply it by 2, we are always going to get an even number. So this part is always even. Now if we add 1 to our even number, so an even number plus 1 is always odd. Therefore, we have proven our conjecture. So we have proven the sum of two consecutive squares is always odd. So we've proven it. We can whack a cheeky little QED there at the end. Okay, jobs are good one for the first one. Okay then, our second conjecture. So for integer values of x greater than 1, x squared minus x is even. So how in the world are we going to prove this? Well, first of all, looking at x squared minus x. Is there any other way that we could write that? looking at it, both terms contain an x, so we could actually factorise and see what happens. So, if we factorise, we would get x times x minus 1. Now, does that help us at all? Well, looking at our two numbers here, we know that x is an integer greater than 1, so x minus 1 is 1 less than x. So actually, x minus 1 and x are consecutive. So, for example, x minus 1 could be 1, and then x would be 2. Now, let's think about what we know about consecutive numbers. Well, the chain, or the pattern of numbers is they go odd, even, odd, even, odd, even, forever and ever and ever and ever. That's how the pattern goes. So, if we have here two consecutive numbers and they are multiplying together, so we got the product of two consecutive numbers, then we know the product of x times x minus 1, it's either going to be odd times even, or even times odd. Now we know either one of these, so either one gives an even outcome. So we know that an even times an odd number gives us an even number, or an odd number times an even number also gives us an even number. We can prove it. Let's prove it. So, this is a little side note, I don't think you would have to do this. So, an even number we could write as 2n, an odd number we could write as n plus 1. So, sorry, 2n plus 1. So, there's our even times odd. If we expand that, we get 2n squared plus 2n, which we can write as 2 n squared plus n, which is always even. So, therefore, x squared minus x is always even. So, we've proven it. Let's work a cheeky little QED on the end. Okay guys, that'll do for this video. In the next one, I'm going to go away and find some nice examples for us to go through. Hope you've enjoyed it. Hope you found it useful.